Okay, there we go, Violent Earthers. We're picking up about where we left off the other day. So to recap a little bit, I don't have our recap spiral, as this is meant to be merged with the material before. But I spent a considerable amount of time talking about early life, or evidence of early life, both in the Urey-Miller synthesis, the hypothesis of panspermia, and also my preferred hypothesis for the origins of life, whether it's here on this planet or on another planet, is relating back to soils, or the primitive gene, the crystal gene, and clays being responsible for being able to house a lot of organic materials and then lead to amino acids. That's basically where we left off the other day at the very end of that discussion. And where that basically led us was to, however the origins of life, whatever your preferred hypothesis is for the origins of life, we have fossil record evidence to suggest, or to show that by 3.48 billion years ago, however it got here, life is here. And life is here in enough abundance that it is disturbing sedimentary deposits and making what are called in the fossil record microbial-induced sedimentary structures, or MISS. And here's an example of a couple of these microbial-induced sedimentary structures. This is not from this article. This is from a separate article that is available on the Canvas site, and I'll make sure that there's a link available in the YouTube notes as well. But here's a couple of examples of these microbial-induced sedimentary structures. Again, had shown these the other day, but these kind of line drawing styles to kind of show us what we're looking at here. Maybe the unaided eye, or the unspecialized eye might not be used to seeing these. But here's what I particularly like about this, is it shows some modern day analogs to these features as well. Because microbes, or the same things that are making these sedimentary structures billions of years ago, are things that still inhabit the earth today, right? And I think there's often this misunderstanding of evolution that in all things, evolution goes from simple to more complex, that we leave behind the things that were simple. Well, if it's simple and it works, then it's still going to work for billions of years. So some of the very same types of organisms, or maybe not genus and species level, but things that are performing the same environmental or ecological niche that existed at this time still exist today. So just because they are ancient organisms doesn't mean that they are extinct organisms. Okay, those two things can certainly cohabitate. So we have modern day analogs for the microbes that were doing the same sediment disturbance as 3.5 billion years ago. And then we have a couple of pictures of the rocks, or field photographs of those rocks, showing the features as if you were walking over some of these sedimentary rock outcrops. You could pick these up and look at those, and the trained eye then would see those as being trace fossils for these types of organisms. And the more you look at Precambrian age rocks, the more often you can pick up on some of these microbial-induced sedimentary structures, depending on, of course, what section of Precambrian rocks you're looking at, and if they're not too heavily metamorphosed. So here's an example of some of these polygonal soil crusts that weren't just mud cracks or desiccation cracks in muds or swelling and shrinking clays, but instead that were maybe tidal marsh, or maybe low, shallow lagoons or floodplains, areas that had some paleosoil or ancient soil type of development on top of them, but also the thin crust of microbes that had inhabited the surface were enough to disturb the distribution of these sediments, that as those microbes captured some of those sediments and then died or were dried out because of their location, as they dried out and the sediment was still left intact in the shapes that those microbes may have disturbed them. So here we have some of these polygonal soil crusts, not that dissimilar to what you might see on desert soil crusts as well, interestingly. Then these biolaminate films, which are a lot more common, I would say, in the rock record. So here you have these biolaminate films of modern day algal accumulations in certain environments. And here we see those microlaminae or biolaminae in the fossil record as well. Let's see. Okay, so this basically catches us up to where we were the other day, and I wanted to make sure to come back to this stage to talk about life and the appearance of life and what that life was really doing here on Earth. What was its, maybe not necessarily, we're not talking about its function as a, how do I put this kind of lightly and delicately, as a purpose, but how was this life functioning? How was it able to do this living thing on this planet that has never experienced this stuff before, or at least for the billion years preceding during the Hadean, as we pointed out, that's fairly inhospitable to this type of life. So two things here. First, how is this life responding to this inhospitable Earth? Or how is it making its niche? What is its function? What is it doing here? How is it surviving? And then second is, in response to this life, this new sphere of the Earth, or this new system on Earth, how is the Earth responding to this? Okay, and I think that those are two really critical questions here that we keep trying to come back to as we move on in Violent Earth. Is how does this, whatever we're talking about, how does this impact life, or how is this occurring, and then how does that process impact the Earth systems in general? Now, thus far, when we've talked about Earth systems, of course, we've used the heliosphere, or the space sphere, essentially, and the influence from the sun. We've talked about the atmosphere and atmospheric chemistry. We'll talk more about that here in a minute. We've talked about the hydrosphere and water, or even sometimes the cryosphere, the ice sheets that covered the Earth. And then also the underlying sphere here is always the geosphere, right? Is always the Earth sphere, talking about the layered Earth and core and tectonics and all that kind of stuff. So those are the four major spheres or elements, if you prefer. And then what we've just done is add in the fifth, right? Which is life, or the fifth sphere, the biosphere or ecosphere, ecological sphere, however you sort of think about that, right? The network or the living community of life of carbon-based materials that are absorbing energy, first and foremost from the sun, or possibly from those hydrothermal vents, some do that as well, and then exchanging that energy through a system, a trophic system, or an eating system, that we sometimes refer to as the web of life, or the food pyramid, things like this. And that's really what life is doing, is it's taking this energy that seems to be freely available, or at least in life's purpose, this untapped energy source, and then it seems to be just distributing that energy source all at the same time, animating carbon. So though this is interesting, what I'm coming back to is the entrance of the fifth sphere now, and that's what we're going to kind of focus on for the rest of Violent Earth. Is we're going to talk a lot more about organisms in the fossil record, and then the place that the violence of Earth has played in the evolution of this fifth sphere, or in the evolution of the biosphere through time. And today begins kind of our excursion into the fossil record then, starting with one of my favorite types of trace fossils. Okay, so whether we're looking at 3.5 billion year old hot spring fossils or 3.48 billion year old microbial induced sedimentary structures in shallow seas, we have very, very good fossil evidence that by 3.5 billion years ago, organisms are living on the Earth, and they are then in turn affecting their environment as well. So the first thing to probably have occurred is the whole diversity or the plethora of life that's out there. So those last organisms that we were just looking at, those could be anything, right? Those could be, well, not anything. They could be classes of organisms that are respiring sulfur. There's sulfur dioxide that's in the available soils, or that's available in the soils, or available in the atmosphere, or available as ions in the water. Maybe there are chemosynthesizers, like those down there at the bottom of the black smoker vents that are using the chemical potential between ions and then bonding those ions. They're able to use that chemical potential energy as their own energy source to then repeat themselves or replicate, right? So my point there is that those microbes of 3.5 billion years ago are very, very diverse. They represent, and we don't know one population apart from the other, but those things represent all of what any biologist or microbiologist could think of as the widest variety of microbes. And only one of those, the whole varieties of microbes, only one sort of class of those would be organisms that are photosynthetic. So you have chemosynthesizers who are absorbing chemistry. You have things like methanogens that are reducing sulfur, and then you have things that are oxidizing carbon dioxide, or that are going through this. That are going through a photosynthesis process. That's where I meant to go. That are absorbing the energy from the sun, this freely available source, and then they're using that as energy source to convert water and carbon dioxide into a sugar, and then also into other sources to repeat themselves. Okay. Now, those photosynthesizers are just one out of, let's say, 50 of those, just to use a number out of a hat. 1 out of 50 of those different types of organisms that are living. But they seem to be very successful. Why? Or why would they seem to be very successful? Because energy, right? This is freely available energy. It's an unlimited resource of energy. So if they're able to tap into and harvest that source, then they could repeat infinitely, right? With just that. Maybe some chemistry is a limiting factor as well, but carbon dioxide is not in limited availability. It's most of the atmosphere at this point is carbon dioxide rich. And water is also certainly not a limiting factor in this, right? Particularly if these are organisms that are living in wet, moist soils, or as those amino acids that we argued formed in soils have slowly migrated to the ocean. So yes, life getting eventually back to the ocean, and as I argued, maybe not originating from the ocean, but going, of course, back to for the rest of the evolutionary process. Okay, so to take a step back here, I'm pointing out that 1 out of 50 of these different branches of organisms are those that are photosynthesizing. Now, along with photosynthesis, what's really occurring here, you're taking energy from the sun, carbon dioxide, maybe dissolved carbon dioxide from either the atmosphere or, of course, from the hydrosphere as it's dissolved in the water, and then water, and using that chemistry, H2O, CO2, and a whole lot of energy, that can make a simple glucose material or simple sugar material that can then be used as a sugar or an energy reserve while going through mitosis or cell division. So that's not the complete picture, though. The complete picture is that, yes, you get this energy, but there's a waste product from this. There's then this other stuff, just like a methanogen might leave behind 2 newly bonded chemistry or chemical ions in its wake. Now, these organisms are leaving behind another substance. They're leaving behind O2, or 2 oxygen molecules that are bonded together. Now, previously, those 2 had been bonded with a carbon atom, CO2, but the photosynthesizers have taken away the carbon, and they leave behind this O2. Now, oxygen, as we saw a few weeks ago, is really prevalent in the Earth's materials, right? Oxygen, as an atom, makes up close to half of the materials available on Earth, or close to half of the atoms available on Earth. So oxygen clearly isn't a new thing, right? Now that's just O. That's just oxygen from the periodic table of elements, O with a -2 charge. But what we're talking about here now is O2, two of those oxygen molecules that are double bonded together with one another, that is brand new to the surface of the Earth. That is not a molecule that had occurred before until this waste product of photosynthesis. So what is identified here in this paper, sometime during the late Archean, bacteria harnessed the process of photosynthesis. And along with photosynthesis then comes the waste product oxygen. And that's in fact why we know that in the late Archean, some organisms had harnessed photosynthesis, i.e., in other words, oxygen started to show up in the environment. Okay? This atmospheric oxygen 3 billion years ago, this paper, is essentially showing that date back to 2.6 to 2.7 billion years ago. They're looking at redox-sensitive metals, or oxygen-sensitive metal, oxygen reduction-sensitive metals, those metals that will readily bond with oxygen to make an oxide mineral. Okay, minerals that didn't exist before because O2 as a molecule never existed before, but it turns out that's a highly reactive substance. Okay, so that led to what's called the Great Oxidation Event, some 300 to 400 million years earlier than previous indications for Earth's surface oxygen. So this is their argument in this paper. We'll talk a little bit about that Great Oxidation Event then. So to now set the scene, 1 out of 50 of these organisms that lived during that time, these multi or single cellular organisms, one of those, or maybe some, had harnessed the ability to absorb energy from the sun and produce oxygen as a waste product. Okay, so if we look at this, how do we know that some of them had invented photosynthesis? Well, going back to that paper, it is the rise of those oxidized minerals in the rock record. So here's on a logarithmic scale. Here, the respiration rate is relatively low in the end. This is the oxygen respiration rate is relatively low. But then at some point we see the rise of that material. We see the rise of oxygen. Then another way to look at that in the parts per million of oxygen in the atmosphere from 3.8 billion years ago to today. This curve is showing, flat line. There's essentially no oxygen in the atmosphere. There's no iron minerals or uranium minerals that are oxidizing under those conditions. But starting at about 2.4 billion years ago, there does seem to be a rise in both of these different models or curves, observations, that there's a rise in oxygen or oxidized minerals. So this is what has always been referred to as the Great Oxidation Event, is that all of a sudden in the rock record we see rocks that have no particularly high iron content to them, oceanic rocks, and then all of a sudden there seems to be these rocks that are iron laden. It's not that all this iron appeared onto the scene, but instead the iron that was floating around in the oceans as an ion, just a regular Fe2 plus or Fe3 plus, the new oxygen in that environment was able to bond with the iron, and then that metal, that new oxide metal, able to sink to the bottom of the ocean to create new layers or new iron-rich formations. Starting at about 1.4 billion years ago and leading well into 1.8 billion or so, where we have a lot of these things. Now, this is from this paper, Reconstructing Earth's Surface Oxidation Across the Archean Proterozoic Transition. So these guys are arguing that This wasn't just a Proterozoic a phenomenon, but this started well into the Archean. And then if you look back at that last paper, they were again arguing that we started to see whiffs of oxygen maybe in particular locations where these iron formations or oxygen-rich formations, oxygen metal-rich formations, started to deposit in some areas before others. So the idea here is going back to, let's say, the primordial soup, right? And you know how much I don't really like that specific terminology of that idea. But I'm now referring to the primordial soup as those shallow seas that have been maybe injected with life after it has already formed here in the soils, those moist soils elsewhere, and amino acids have formed, and you get early life. And these shallow seas would be a great place for life. I mean, also the ultraviolet rays from the heliosphere at this time were able to bombard early life and kill early life. So you either need soil as the protector, or you need water as the protector from those ultraviolet rays. So either way, these organisms that are now living probably in water, or let's go back to the proverbial primordial soup idea, only some of the entire Earth has some of these pods of perfect conditions for these organisms to live in such abundance that they're producing so much oxygen that these iron formations are occurring, or these iron formations are absorbing oxygen and then forming iron layers on the bottom of the ocean. So about 3 billion years ago, the question mark here is suggesting that we do have some fossil record evidence, traces of these iron formations as old as these. But it wasn't until about 2.5 billion years ago that we see these in almost every section of that age of rock. So clearly showing that this is a global phenomenon now and not just a localized phenomenon. I hope that makes sense. Going from this occurring in just small pockets or small areas to being a global thing. Or think of that as this maybe similar to the spread of Homo sapiens or the spread of our species localized in a very small area in Africa first, and then spreading circumboreally. So at first, the fossil record evidence would suggest that Homo sapiens are just in this small exclusive area, and then 100,000 years later, they're showing up in multiple locations around the world until 100,000 years later, yet again, they are all over the earth. So similarly, these photosynthetic bacteria are very successful, right? I mean, how could they not be? They're tapping into a completely free energy source that is unlimited and abundant, along with the other two things that are very abundant on Earth, or two other things that are abundant on Earth: carbon dioxide in the atmosphere and water of the hydrosphere, right? Now picking up some of that carbon that's also available in the atmosphere at this point, and then that rich energy from the sun. You have a global or circumboreal type of organism, the photosynthesizers, that are really starting to affect the environment. How? Well, in this case, they're affecting the environment by oxidizing iron out of the water and that accumulating in the rock record. So that's clearly an effect to the environment. They're taking out iron out of the environment and making rocks out of it, right? Or making minerals out of it. Also, they're putting oxygen into the environment. O2, a brand new substance that had never been experienced here on Earth. Okay, so this is a decent diagram to kind of show what is going on here. And I think this is really worth drawing out as well. I'm not sure how well my camera is going to capture this today. But we'll try this out, and then I will try to upload a self-drawn diagram to this as well. But it's worth going through the story here. So let's see, how far over can I go? I can go about this far, and that's it, huh? All right, so starting off with, let's say, just a continent, and then down into a shallower ocean. Okay, so here's some waves of an ocean. And then, of course, we need a nice bright sun in the sky. Super happy. Okay, so here's, the soils that I would argue are the cradle of life, and then here's a shallow sea where we have a lot more of these organisms that are clearly living in the oceans. We do have microbial-induced sedimentary structures to suggest that. What's happening here for literally billions of years by this point, the hydrosphere cycle of water evaporating into the atmosphere and making clouds that then rain down on the geosphere are liberating elements here, or they're chemically weathering down substances here, rocks, to make clays, or to make those soils that we talked about a bit ago. And in part of that process, that is taking ions that are in solution, and they're going down the river system out into the ocean. Okay, so this is the hydrosphere cycle, and along with that hydrosphere cycle comes some of the lithosphere into the ocean. So now you have ions that are floating around in the ocean. This is how you go from an early Earth's ocean that has essentially no salts within it, and the ocean gets saltier through time, or more and more ions through time. So you have maybe some, let's start out with, you have some sodium ions, calcium, you have some other things, of course iron being one of the favored in this situation, and potassium. So point is, you have all of those elements that we talked about very early in the class that are being weathered and broken down and dumped into the ocean as their raw ionic form. Now, along with those, of course, there's abundance of other anions too. There's colloidal silica, SiO2. There's probably some chlorine, things like this. But I'm going to avoid clutter, I'm going to leave those out. In fact, I should go ahead and erase potassium and sodium and calcium because they're not necessarily important for this conversation. Now, the other thing that's going on here is these organisms that are photosynthetic are living in the ocean. Okay, there's just a couple of organisms there in green, not to be confused with the land surface here in green. And what those organisms are doing, the light from the sun that's striking them, that's their energy source, little E negative there. And then they are also absorbing water. Okay. And maybe a little bit of carbon dioxide from the atmosphere. Okay. Now I should say one thing. So here's your trifecta of photosynthesis then, right? Light, carbon dioxide, water. I should make one mention here. How are they pulling out carbon dioxide out of the atmosphere if they're in the water? Well, let's point out that water or liquids and the atmosphere are in chemical equilibrium with one another. This is the, I always forget the name of this chemistry law. This might be the law of vapor pressure. Anyhow, think about what happens when you open a bottle of soda or a carbon dioxide or carbonated beverage. All of that carbon dioxide that was stuffed into that liquid or injected into that liquid and then is held under pressure, as soon as you release the pressure from that, the amount of carbon dioxide that's in that vessel is much, much higher than the amount of carbon dioxide that's in the atmosphere. So there's a natural chemical equilibrium for that carbon dioxide to exsolve out of that substance and then go into the atmosphere, or exsolve into the atmosphere from the liquid into the gaseous phase. Well, it's still in a gaseous phase in the liquid, but what I mean is to go out of the liquid into part of the atmosphere. So that process of having the same, or liquids trying to have the same level, or at least a consistent level of dissolved gases as the composition in the atmosphere is really common, right? We see it with a soda. You can see it with any glass of water or carbonated beverage, something like that. I guess carbonated beverages are like my go-to example then, right? So my point here is if you have say pure water with no carbon dioxide within it in a room or in maybe a small enclosed system that you pump carbon dioxide into and you increase the gaseous amount of carbon dioxide, then the water will start to absorb some of that carbon dioxide because water is a solvent, as a dissolved material. So the atmosphere and the hydrosphere, the ocean in this case, have some sort of chemical equilibrium to them. So if you have 90% of the atmosphere is carbon dioxide, well, then the ocean, 90% of its dissolved gases are also going to be carbon dioxide. Okay? It's going to absorb that material. So naturally, you already have carbon dioxide that's in the water. Okay? So here's back to our organisms. They have taken in carbon dioxide and water and energy from the sun, and wow, great! They make they do the wonderful photosynthesis process. But what they leave behind then is a little bit of oxygen, O2. Okay, a brand new molecule, as I've said a number of times before. Now, that brand new molecule, again, is highly reactive with metals that need 2 more electrons in their orbital shell. Things like iron, things like uranium work really well. So here's all of this iron. Remember, iron is the 3rd most abundant ion or molecule, or atom of Earth. So this whole erosion process that's occurring here, it's just dumping iron into the ocean. You have an iron-rich ocean by this point. But now that oxygen is being released by those organisms, guess what happens? These two things, the iron and the oxygen, they bond together to make something like an FeO, we'll just put an X here, FeOX, or an iron oxide mineral, just in general. Those can be things like magnetite or hematite, both of those iron oxides, magnetite and hematite. Okay, those magnetite and iron, or magnetite and hematite, those are solid materials then, right? Those are crystals. And because solids, as a crystal, is more dense than the liquid surrounding it, those solids sink to the bottom of the ocean. And because there's so much of this going on, again, there's a ton of iron that's already in the water. If there's a ton of organisms that are producing oxygen as a waste product, then all of that makes magnetite or hematite, and it sequesters at the bottom of the ocean. So you end up with these really thick bands while the community is nice and healthy, partying down, replicating like no other, producing oxygen, farting out the back end and burping out all this oxygen, is making these very thick bands of magnetite-rich sediment or iron-rich sediment. Okay, now this is really cool. This is the appearance in the rock record by being able to see these oxygen and iron-rich layers. That's showing us that oxygen is present in the Earth's system now. O2, respirable oxygen, which it wasn't before. Now let's back up a little bit to those photosynthetic organisms. Remember, these photosynthetic organisms, or the blue-green algae, oxygen is their waste product, right? Waste product. Now, what happens if the community is so large and they're defecating all over, right? They're expelling their waste in their environment, and then their waste builds up. and builds up and builds up and builds up. Yes, in some cases, maybe on the periphery of the community, that oxygen is reacting with iron and is forming banded iron formations. But let's not forget, this is a waste product to them. It's toxic to them. That's why they want it out of their bodies. It's lethal. So eventually, by maybe means of poisoning, okay, or by means of just lack of access to the sun or some other means, the community eventually collapses. The community that was producing the oxygen stops producing the oxygen. I like to think about it as they poison themselves. They die, right? And once they die then, what's then deposited on the ocean floor is just iron-rich sediment. Okay, it's not iron oxide rich anymore. It's not hematite, it's not these magnetite anymore. It's just all of that silica dioxide that was being shed off of the continent, and that's not doing anything. It's not reacting with iron at all. Now, because of the pH of this environment, the silica dioxide is now precipitating and forming layers at the bottom of the ocean. So you get these red layers of silica dioxide with iron. With iron. Those are also called chert layers, red chert or jasper. Okay, then that community of organisms that had previously died and gone away, remember this is a global phenomenon, so it's not like the organisms just went extinct in this one location. Maybe most of them died, 90% of them, 98% of them. But from those 2%, they replicate like rabbits, and they come back, and they begin to proliferate again and put oxygen in their environment again. And guess what happens again? More iron oxides sequester at the bottom of the ocean. Okay? Well, then they proliferate too much, and they put poison into their local environment, and then they die. Okay, you see where we're going with this? Alternate bands of iron and jasper, iron and red chert formations. Red, black, red, black, red, black, red, black. That are showing us this delicate dance of this community between sequestering iron in the environment and partying by putting out oxygen in the environment, and then killing itself by over-partying, right? Or like a kind of an extreme oxygen overdose situation. All right? So these are what are called, and I haven't meant to avoid the term by this far. I don't know if I've said it though. These are called banded iron formations for clear reasons, right? Banded iron. And it's a formation of rock, and it's bands of iron. Okay, pretty darn clear. So here's an example of these banded iron formations. I've meant to show this rock probably a few times by now, but hopefully that shows up decently well in the video with the lighting there. You can see that. I don't know if that'll change anything. A little bit. You can see the alternating bands between some of these darker bands and the more reddish bands. Okay, here's a couple of magnets that show that this is a magnetic material. Okay. Okay, magnetic material. It's the dark bands here that are full of magnetite. That's why it's named magnetite. It's a magnetic iron mineral, Fe2O3. And then between those, the reddish layers are non-magnetic iron-rich chert, or jasper, it can also be called. This is a sample from northern Minnesota, from the iron ranges there, and this is about a 2.5 billion year old rock. This is in an area, the craton of North America, the superior craton, right? We had discussed the supercontinent cycle quite a ways back, and that craton of North America, on the edge of that craton, or perhaps in a rift that formed in that craton, was an area that has shown to be a nice area for the proliferation of this type of life that's producing the oxygen to form a banded iron formation. Okay, this is one of my prized samples. I really, really love this thing. I wish I could give it to you to hold it, right? So you could touch it and you could feel how awesome this material is, and also really heavy. This is a very heavy sample. It's an iron-rich material, of course. Okay, now, so this is the story of banded iron formations then. I have so much to say about these, right? I absolutely love this story, for one. So let's talk about that, the story aspect, for a minute. I think this is a really, really exemplary aspect of how the Earth systems work together. Okay? The four Earth systems, you have the heliosphere, the atmosphere, the hydrosphere, and the geosphere, and then now we've added in life, or the biosphere. The heliosphere in this context, that's the sun providing the energy, right? The atmosphere has contained all of those gases, right? The carbon dioxide gas, or in this case, the gas that's been dissolved into the ocean, but it's still gas. It's still part of that hydrosphere, or that atmosphere. The hydrosphere, of course, the water that's needed for this reaction. And the result is a record in the geosphere, or the actual result after life has manipulated those other three systems that produces some geospheric material. To me, this is one of the most profound examples of how the Earth systems are all working together, or how they have worked together in producing themselves, or changing or transferring energy between these different gradients. This is very similar to it's the second principle of the bigger ideas, right? That the flow of energy drives the cycling of matter. Okay, I think that's really, really cool. Now, another thing that's really neat here is this rock that's full of oxidized iron. There was only one time in Earth history where Earth didn't have oxygen. And then at 2.5, or about 3 billion years ago, 2.5 billion years ago, 1.9 billion years ago, that whole kind of billion-year span, we went from no oxygen to afterwards oxygen forever. The Earth has been oxygenated ever since. Okay, it's never gone away because of organisms, because of photosynthetic organisms. They have also never gone away, and they continue to produce oxygen in the environment. So this rock is, well, I guess it's rare, right? This rock, it shows this story. This is our evidence for this type of phenomena, this story, this geologic event that occurred. But also, this rock will never form again. This is one thing in geology that is a type of material that formed only once, and it'll never happen again, right? Glacial till. Well, that's happening right now, right? Limestones, they're sequestering right now. Sandstones, they're occurring right now. Rhyolites, they're occurring right now, right? All of the other geologic materials that we've talked about are things that have happened for billions of years and will continue to happen as part of Earth's business as usual processes. But when life showed up on the Earth, well, about 1 billion years after it showed up, it changed the face of the Earth enough that it produced a brand new material that made a brand new rock, and a rock that will never form again. That records the rise of oxygen. Okay? Sometimes we call that the rise of atmospheric oxygen. Why atmospheric? So far we've really focused only on the sea. Well, remember that the oceans and the atmosphere are in chemical equilibrium. You pump a bunch of oxygen into the ocean, eventually it's going to get super saturated with that, and it's going to exsolve into the atmosphere. So slowly, right, the atmosphere begins to become oxygen rich. Well, what happens to the continents then? Those continents then undergo an oxidation process as well. All of the exposed iron, all of the biotites, all of the pyroxenes, all of the olivines that are there weathering on the surface, there's a brand new substance out there to chemically erode those things, and it's called oxygen. And it's something that happens to us all the time, right? You have a piece of iron, or you have a shovel that you've been digging in the dirt with. You get it a little bit wet, and you leave it out overnight, and the oxygen corrodes it. The oxygen oxidizes it and forms rust. It's still happening today that Earth substances are oxidizing, especially when we reduce them to their metallic parts. Okay, so there's two really cool parts of this story, I think. Number one, just the interaction between all the systems. As an Earth system scientist, I think that's one of the most brilliant examples that we have available to us of the inner working of the systems. Then secondly, just how rare this material is. It's a material that formed once and isn't ever going to form again. The Earth is oxygenated and it's never going away, right? I mean, as far as single cellular photosynthetic organisms or multicellular organisms are still around, right? Okay, then the next interesting thing here is what happened to all of those organisms that didn't photosynthesize, right? So you have remember I pulled a number out of the hat and said 50. So 1 out of the 50 organisms at this time were photosynthesizers. Well, oxygen is also poison to the other 49 of them, right? So you have the photosynthesizers that are producing oxygen, and they're clearly killing themselves sometimes, but they're also killing everything else. The rise of oxygen was the rise of the poisonous gases on Earth that killed everything off. Well, maybe not everything, clearly not everything. Things made it through that were able to withstand the oxygen-rich environment, which was the photosynthesizers, right? Through evolutionary means or natural selection, as they kept pumping oxygen into the environment, the photosynthesizers had to deal with this new poison. And therefore, through generations and generations and generations, they were able to build up not necessarily a tolerance to this, but build up the genetic code, the genetic material, to withstand this being such a corrosive or poisonous process, because they were exposed to it all the time. The other 49 organisms that don't produce oxygen, that don't photosynthesize, deader than a doornail, right? Maybe not all 49 of them. Today we still have methanogens and chemosynthesizers and other extremophiles. So they're not completely gone, but a lot of organisms that probably existed during that time were poisoned off by the banded iron formation event, or by the rise of atmospheric oxygen, which has led to something that we are very proud of, right? Which is us and plant life and so on and so forth. But that was the ultimate fate of many of Earth's early organisms, was they suffered the very first mass extinction. Now, we don't have fossil record of that extinction, but reading between the lines and looking at how extreme this event must have been, that was very likely the very first kill-off or extinction event on Earth to organisms. Okay, oh yes, I did mention this was from Minnesota. I was here with a class a few years ago, just outside of the Sudan mine, an older mining area, and looking at some of these wonderful, wonderful banded iron formations. You might ask the question really quickly, why aren't these in layers, as I showed them in the diagram before, drawing up on the board? Well, they're in layers, excuse me. Why aren't they in straight layers? These sediments have undergone 2 billion years, 2.4 billion years of Earth processes by then. These were actually involved in the Grenville orogeny. They were also involved in the margins of the Great Continent Rift, or the Mid-Continent Rift. So they've been tectonized quite a bit. Now that's not the sole reason why they're all folded. These are still sediments. They haven't been metamorphosed much. But some people do suggest that a lot of this deformation is what's called soft sediment deformation. So as sediments are laying down and they're still relatively soft, even if they're undergoing the lithification process, they're still relatively soft. They haven't been cemented together. If an earthquake occurs and these things get jumbled up, not so jumbled up that they mix,
but just jumbled up enough that they shift around, that causes soft sediment deformation. So it's been suggested that this isn't just compressional tectonics, that it's also some amount of soft sediment deformation as well. So, all right, wonderful place in looking at iron formations. Now, that was just an example from up here, the Lake Superior region. Look at all these triangles, right? This is a global phenomenon of these banded iron formations of this type that are found throughout the world. Areas in South Africa, areas in Australia, South America, of course, North America, the subcontinent of India, areas of China, areas out there in the stands or at least in Siberia. So they are a circumboreal material. I don't know much about the discovery of these in Antarctica, about iron-rich sediments, but the limiting factor there is it's covered with ice, right? So I don't know if we know a whole lot about the Paleozoic, or sorry, the Proterozoic Archean age rocks in Antarctica. I certainly don't. So this is a global phenomenon that's occurring. This is how we then know that rise of atmospheric oxygen that occurred 3 billion years ago was more of localized phenomena, but now this is a global phenomenon. If this is a global phenomenon, again, going back to mass extinction, organisms that couldn't withstand oxygen, that it's a poison, they're dying out, they're going away. Also, minerals or rocks that are susceptible to oxygen are corroding away, or they're forming, they're oxidizing away, or there's the banded iron formations that are forming. So there's several Earth systems here that are changing. The biosphere itself is changing because of oxygen. The geosphere is changing because the atmosphere has a new component to it. It was mostly carbon dioxide, but now that carbon is getting sequestered into the biosphere and replaced by oxygen that has a new chemical relationship with some of the continents here, and that's an oxidizing or a chemical weathering relationship. So stuff is changing here in the Earth systems, and it's changing like it has never changed before, and frankly, it hasn't changed like this after. This is one of the biggest events that has changed the organization of those systems, right? I mean, you can't change much more than going from 4 fundamental systems to adding in a new system, the biosphere, okay? And really, we've had the biosphere then for this entire time. Until another sphere of the Earth arises, that's maybe when we will see the same types of changes that we're seeing here. So what other changes are occurring? I should call out this video. It's, of course, available in the show notes. This is a really good, just a couple-minute video from Ted Ed, how single-celled organisms almost wiped out life on Earth. Of course, discussing the first mass extinction then, right? And I think this does really, really well to show the entire story as I've showed it as well. Now, that great oxygenation event has